All right, good evening, everyone. Welcome to the lecture for this week, the first lecture for this week. I do not currently have any live attendees at the session, but I just wanted to do a recording for you guys so you'd have it to watch at another time. So if you're following along in the course notes and watching these in order, you'll probably notice that I'm going to go a little bit out of order this week, and I'm actually going to likely end up adding a third lecture session this week, just because we have a lot of information to cover and it's a little bit more of the challenging stuff. So I want to make sure that I give each section its due amount of time. So in this lecture tonight, I'm going to talk about the lives and deaths of stars. And that's going to be sections 2 and 3, I believe, of your course notes. And then on Wednesday morning, I will talk about quantum mechanics, and then I'll finish up with talking about things like black holes and relativity and that kind of stuff at a time that I'll need to send out an announcement when I decide when that last section will be. But I just wanted to start with lives and deaths of stars today. So the first thing I want to do is talk about what it means to be a star. So we're going to be building up to a star on something called the main sequence. This is where a star spends most of its life. It's a stable star, and that's mostly what we're going to look at. But the first thing I want to do is look at what it takes to become that. So I've labeled this star goals, and as I talk about the process in which a star is formed, I want you to keep these star goals in mind. These are things that stars have to be in order to become a stable star. So the first thing is to be in a type of equilibrium that we'll define later as hydrostatic. And that means that the star is not going to be shrinking, it's not going to be collapsing, it's not going to be getting smaller, and it's also not going to be expanding. And then the second thing is that the star is going to need to have a core temperature of a minimum of 10 million Kelvin. So a star is going to be hottest at its core. And this is not the surface temperature, this is the temperature in the center of the star. So it needs a minimum of 10 million Kelvin. And then the last one is to maintain a constant temperature on the surface. So this means that it's going to not increase or decrease in temperature. It's going to shine at a constant rate. All right, so just keep those things in mind as I go through the process of the formation of a star. So if you've ever read about or looked into astronomy before, the focus was probably on a lot of celestial objects, things like stars or planets. But there's a super important region of space that is often overlooked, and that's known as the interstellar medium. This is, as it might sound, interstellar means between stars. So this is pretty much what we've referred to as the vacuum of space so far. And it is almost a perfect vacuum. It has a very, very low density, almost to the point of being a vacuum, certainly better than anything that we've ever produced on Earth. But even though there's almost nothing in it, it's important to start our discussion here. And the reason why, well, I have three important reasons. The first one is that there's as much mass in the voids or the places in between the stars as there is in the stars themselves. So even though the density is incredibly low, the volume of interstellar space is so vast, there's so much of it, there's so much space in between in between celestial objects that it adds up to an incredibly large amount of mass. And then the second reason is that stars are born here. So obviously that's going to be super important for our discussion today as we talk about the formation of stars. Stars have to be born out of something. They're born out of the interstellar medium. And then the last thing is kind of a cyclical process, as we'll see by the end of lecture today. But stars die here as well. Low mass stars will give off a planetary nebula. They'll give off gas and dust out into the interstellar medium. High mass stars are going to explode in a supernova explosion, and those elements that made up the star are going to again be dispersed out into interstellar space. So This picture that you have here, this is, you might recognize, it's actually a mosaic of photographs, and it shows a panoramic view of our Milky Way galaxy. So the bright regions of this picture are going to be lots and lots of stars. It's made up of thousands of collected unresolved light from distant stars. In the dark portions of the picture, that's going to be your interstellar matter. These are not simply holes in the stellar distribution. This is not where there aren't stars, but instead it's just going to be regions of space where interstellar matter is actually blocking the light from the stars beyond it. So if the interstellar matter was not present, then the Milky Way would appear as like a bright band of light, unresolved light across the sky. So the interstellar matter, those things are gas and dust, is collectively known as the interstellar medium, and it consists of those two main components of gas and dust. The gas, Trayvon, yeah. Oh, welcome. I didn't even see you pop in there. Yes, there's mass in space itself. It's trillions and trillions and trillions of times less dense than any massive object in space. But there are individual particles and molecules in between stars that makes it not a perfect vacuum, but it's very, very close because the space in between those individual particles are so spread apart. Great question. So it's made up of these very small individual atoms and small molecules. And that's going to be the gases. And then the dust is going to be a little bit larger. That's going to consist of more clumps of atoms or larger molecules. And you can kind of think about this as the dust in space is kind of like a smoke or a soot. But interstellar matter is not evenly distributed throughout space, so it's actually denser in some locations than others. Our sun and our solar system are actually located in an incredibly low density region of space. It's called an interstellar bubble, and ours specifically is called the local bubble. And this means that radiation can easily pass through space here without being impeded by that gas and dust. And because of our location inside of this bubble, this very low density region of space, it gives us a unique opportunity to detect a lot more stars than we usually would, especially as it turns out in the ultraviolet range, because the bubble is virtually transparent to ultraviolet radiation. So we have a unique position in space. We wouldn't, if we were elsewhere in the Milky Way galaxy, we might not be able to see as many stars as we can because of that interstellar gas and dust. So we're in a low density region of space, but there's also going to be higher density regions of space as well. And those are going to be known as interstellar clouds. Interstellar clouds are going to be the key. They're going to be the starting point of our star formation. So star formation happens when part of an interstellar dust cloud begins to contract. And as you might guess, this doesn't just happen out of nowhere. It doesn't happen on its own. So let's look at how this might occur and what might cause it. So the first thing we want to do, like in the picture here, is consider just a few atoms that are floating out in interstellar space. When we look at them and consider the gravitational force, it's not strong enough to really do anything. It doesn't pull those atoms together because they're so small that they don't have a lot of gravitational pull. And they're definitely not strong enough to overcome another force that's acting on them, which is the heat, the random thermal motion. So when the random motion of the heat brings those atoms close together, then they start to be pulled together by gravity, but then it's just not enough. There's not enough atoms to make a significant amount of mass to have that gravity take over, and they're again taken over by heat and scattered in different directions. But if we continue to increase the number of atoms, if we go beyond the 5 that we see in the picture here, then the gravitational attraction is going to start to increase. We know that if there's more mass, then there's more gravitational attraction. And eventually, the collective gravity of those clump of atoms is going to be strong enough to prevent it from dispersing by its random thermal motion. So how many atoms does it take in order to make this happen, to make them not disperse into interstellar space? The answer is going to be about as many atoms as we have in the sun, coincidentally, and that's about 10 to the 57 atoms. If our hypothetical clump of atoms is more massive than 10 to the 57 atoms, it will not disperse, and its gravity is going to cause it to contract and ultimately form a star. So, like we said, 10 to the 57 atoms are not just going to clump together by chance. It's generally going to be triggered by some sort of catastrophic event that pushes the massive pocket of gas squeezed together. And there's a couple of different things that might make this happen. There could be a shock wave that's produced when a nearby group of stars form and then heat their surroundings and create something called an emission nebula. Or there could be a nearby supernova explosion, which could push the gas together and force those 10 to the 57 atoms together. And then another option is maybe the thermal energy is reduced. Maybe the star becomes cold for some reason, and it loses heat and then allows gravity to take over because the random thermal motion is not as strong. So whatever the cause, theory suggests that once the collapse begins, then star formation is going to inevitably follow. So if you look through your course, well, I guess you couldn't have looked through your course notes yet because they're not open until midnight tonight. But in your course notes, we're going to go through each of the different stages of star formation and talk about how long it spends in each stage and what each stage consists of. So in stage 1, this lasts about 2 million years, and during this time, the cloud is going to contract, and as it gets smaller and smaller, it breaks up into smaller pieces due to gravitational instabilities in the cloud. Those are known as Jeans instabilities, which we don't really get a whole lot into in this class, but just know that there's gravitational instabilities that causes the cloud to fragment into smaller clouds. A typical cloud will break up into hundreds or even thousands of smaller clouds, and they're each going to imitate the behavior of the parent cloud, meaning that they're going to continue to contract and get smaller and smaller. So that's stage 1. The object is still an interstellar cloud, and it's just starting to fragment into smaller and smaller pieces. You'll notice that it's still fairly cold, even at the core, and the surface temperature only about 10 Kelvin, and the density is relatively low, and the diameter is very, very large. So as it contracts, it continues to fragment, and the process of the cloud fragmenting into smaller pieces over and over and over again will eventually be stopped in stage 2. And in stage 2, the density of the shrinking cloud pieces actually gets high enough that the radiation from inside the cloud cannot escape as easily. So the radiation becomes trapped, and that in turn increases the temperature and pressure of the cloud fragment, and the gravitational instabilities will then subside. So the cloud fragmentation stops, but it still continues to contract. In stage 3, about 100,000 years after it first started contracting, the stage 2 cloud fragment has now shrunk into a gaseous sphere, so it kind of starts to look a little bit more like a star than a cloud now. And it's still going to be very, very large and relatively cool, although it's heating up as it starts to collapse. The diameter is about 10 to the 10 kilometers, which is going to be roughly the size of our solar system. So you can imagine something that kind of looks like a star extending out to Pluto's orbit. At the start of stage 3, the inner regions have become completely opaque to their own radiation, and this allows it to start heating up considerably. So you can see from stage 2 to stage 3, although the temperatures are still relatively cool for what we need, our 10 million Kelvin that we were looking for at the beginning, you can see that the jump in the central temperature from stage 2 to stage 3 goes from 100 to 10,000. And that's because of that density increasing to the point where the star is opaque to its own radiation. So for the first time here, the fragment starts to resemble a star, and therefore we change the name at this point from a cloud or a cloud fragment to a protostar. So protostars are the dense, opaque center of the cloud fragment. The mass is increasing more and more as more material is pulled down onto the surface by its gravity, but is still getting smaller because of its internal heat is not strong enough to overcome the relentless pull of gravity. So by the end of stage 3, we can now establish that there's a surface of this star. All right, so you can see how this process is kind of keeping going. It's getting smaller, it's heating up, it's getting denser. So as the protostar evolves, its density increases, the temperature rises, both in the core and at the surface. And the core has now reached a temperature of about 1 million Kelvin by stage 4. At this temperature, the electrons and protons at the center of the star are going to be ripped from their atoms, and they're going to be flying around the core at really high speeds. So there's going to be a lot of activity in the center of the star, but it's still not enough to make it to make our ultimate goal, which is about 10 million Kelvin. So the size, 10 to the 8th kilometers, it's now smaller than the solar system, but it's still much larger than the sun. So it's going to extend out to about what we have now is Mercury's orbit. By this time the stage 4 is reached, our protostar's physical properties can be plotted on a very important chart in astronomy that you see on your screen here. And this is called the HR diagram. It's called the Hertzsprung-Russell diagram. And this is something that maps the stellar evolution of a star. So we're going to be referring to it and showing you different stages of a star's life as we go through this lesson, and then also the deaths of stars later. So at each phase of a star's evolution, we put a point on the diagram, and that represents a star's surface temperature, which is listed across the bottom of the diagram, as well as its spectral classification, which goes along with its surface temperature. The hottest stars are O-type stars, as you can see the very left of that diagram. And then our coolest stars are going to be M-type stars. Our sun is a G-type star, and that shows us that it has a surface temperature of about 6,000 Kelvin. So we can follow the plot downward to the x-axis of this chart, and that'll show us what the surface temperature is at any given point in its stellar evolution. So the motion of this point around the diagram as a star evolves is called its evolutionary track. So this is a graphical representation of a star's life. It has to do with its age and the type of star that it is, but keep in mind that it has nothing to do with actual real space motion of the star. This isn't tracking the motion of the star through space. It's just showing you different ages of its life. All right, so stage 4 is where we start putting that on the HR diagram. And then in stage 5, our protostar is still not in equilibrium, even though its temperature is now high enough that the outward directed pressure has become a powerful counterforce against gravity's inward pull. The balance is still not perfect. So as a result, it's starting to slow down in its collapse. The contraction has slowed, but it doesn't stop completely. So it's still getting smaller, it's still getting hotter. We haven't quite reached our equilibrium yet. In stage 6, the core finally reaches our goal. We have reached our star goal, which is 10 million Kelvin. And then the fuel of stars, this thing that keeps a star stable throughout its entire life on the main sequence, nuclear fusion can begin. I'll talk a little bit more about what nuclear fusion is in just a second. But right now, let's just notice that after 30 million years since the cloud has collapsed, the central temperature of the star is now 10 million Kelvin. We have reached our goal, and we can now say that this object is a star. Stage 7, it's not quite to main sequence. It's stable, but it still needed a little bit more contraction in order to become fully stable, and it will stay on the main sequence for the majority of its life as long as it has enough hydrogen to complete nuclear fusion in its core. So we have now met our star goals. Step one, we're in equilibrium. We're not shrinking or expanding. Our current sun has a diameter of about 1.5 times 10 to the 6. It's not getting any smaller. It's not getting any larger while it's on the main sequence. The core temperature has a minimum of 10 million Kelvin, where it has stopped is about 15 million Kelvin, which is plenty to ignite fusion in the core. And then it maintains a constant temperature on its surface. So this means that it's producing as much heat in the core as it's giving off at the surface, and allows the star to shine as bright, shine a consistent brightness and maintain a constant temperature on that surface, which is about 6,000 Kelvin. And that brings us to a main sequence star. So let's look a little bit closer at these star goals now that we have reached them. So a star spends most of its life on the main sequence, which is about 10 billion years. Our sun is currently at about 5 billion years, so it's a middle-aged star right in the middle of its stable lifetime. So there are three main components that a star needs in order to be on the main sequence. And we already said equilibrium, but let's define those types of equilibrium. The first one is hydrostatic equilibrium. This is the balance between the internal thermal pressure pushing outward and then the weight of the material pressing inward towards the center of the star due to gravity. So remember what equilibrium was from our discussions in week 1. That means that there's a net force of 0. There's forces acting in opposite directions and they're equal in magnitude, so that there's no acceleration in either direction. And in this case, it's no acceleration to expand or acceleration to contract. So gravity is a little bit easier. We've already kind of talked about that. Gravity is the force that is always pulling the mass inwards towards the center of an object. We talked about Earth's gravity. Everything is always being pulled towards the center. And with the sun, the same thing. Gravity is always pulling the mass of the star towards the center. So in order to make it so that the sun does not collapse, then there has to be an outward force that is opposing that gravitational force that's pushing inward in order to keep the star at its same size. And that force is the pressure that comes from the internal heat produced by nuclear fusion. So hydrostatic equilibrium, in easy terms, just allows a star to maintain its size. And then the second type of equilibrium is thermal equilibrium. We're going to focus more on hydrostatic equilibrium for our discussion, but thermal equilibrium is important as well, obviously. And thermal equilibrium is what I was just talking about a little while ago, which says that the energy production at the core of the star is going to equal the energy loss at the surface of the star. So in other words, the star shines at a constant rate. This allows the surface temperature to remain the same. The luminosity of the star is going to stay constant throughout its life. So hydrostatic stays the same size. Thermal equilibrium stays the same temperature and brightness. And then finally, in order to be on the main sequence, and we've already kind of mentioned this a few times, a star's main energy source has to come from the center of the star, which is the process of nuclear fusion. Nuclear fusion is taking hydrogen in the core of the star and slamming it together at really high speeds and ultimately producing helium. So you can see the process here. The details of this are not super important to us, but basically what you need to know is that when hydrogen atoms are forced together at really high speeds, they fuse together. And when they fuse together, the resultant helium atom is actually less mass than the original 2 hydrogen atoms added together. So there's some excess mass in this process. And we learned from the law of conservation of mass and energy and about our mass energy equivalence, E equals mc squared, that if there's extra mass, that mass has to go somewhere. And it's actually given off in the form of energy. So that energy travels to the surface and fuels the star. And this is a really good process. It happens for a long time. It keeps the star very stable. But there isn't an infinite amount of hydrogen in the core. A star can't do this forever because eventually it's going to run out of hydrogen. So we know what happens to hydrogen in the core now. But a natural question that you might come to is, well, what happens to the helium that it fused into? What happens to that helium after it has formed? Well, the answer for right now is not much. The temperatures in the core of the star are not hot enough to make helium begin fusing. So we needed to reach a certain temperature in order to accelerate the hydrogen atoms at the core of the star to a high enough speed so that when they smash together, they would fuse together. Heavier elements, hydrogen is the lightest element on the periodic table, lightest element in the universe. Heavier elements are going to require more speed, more energy, and therefore more heat, a higher temperature, in order to begin a fusion process. So the temperatures in the core of the star now are not going to be hot enough for helium to begin reacting at all. So it just kind of sits there, not really doing anything as an inert gas, kind of like ashes building up in a fireplace, and just gaining more and more mass as hydrogen continues to fuse into it. So eventually, much later in the star's lifetime, the core is going to have gained a lot of mass due to the heavier helium pile, and it's going to start to gain its own appreciable gravitational pull. So much so that when the nuclear reactions begin to slow, when it starts running out of hydrogen, then the core is eventually going to begin to collapse. So the pictures that you see on screen here are showing that the where these reactions occur are in the core, and the helium content remains the same pretty much everywhere else. If you can see in picture 3 there, we follow those arrows down. The helium content remains the smaller percentage looking at the star overall, but it increases to about 100% when it runs out of hydrogen in the core. All right. Any questions, Trayvon? All right. So when the hydrogen is all converted into helium, then, as you might guess, there's no more fuel and the nuclear reactions will stop. So if you think about that relationship, that hydrostatic equilibrium, you had the core producing the heat that's pushing outward, you have gravity pulling inward. If that outward force stops, then gravity is going to take over and the core is going to start to shrink. So the core collapse is going to cause the layers outside of the core to begin to collapse as well. Gravity is going to take over not only at the core, but at the layers outside of it. And as they collapse, they begin to heat up. And they heat up so much that eventually they're going to get hot enough for nuclear fusion with helium to begin. And it can happen in the layer just outside of the core. So this process is going to be called shell burning. And it brings our star out of the main sequence. We've gone our 10 billion years fusing hydrogen into helium. Now we're outside of the main sequence in something called the subgiant phase. So we have 3 layers to our star now. We have a collapsing, non-burning helium ash of a core. We have a hydrogen-burning shell, which is immediately outside of that, and then a non-burning envelope of gas that's surrounding them both. So hydrogen continues to burn in a shell around the core, which produces more energy than is needed to support the star at its current size. So the star has left hydrostatic equilibrium and the outer envelope begins to expand. So the gas envelope surrounding the core is going to expand, it's going to puff up, and it's going to puff outward under the action of this extra pressure. So now the pressure that's being produced right outside of the core is going to be greater than the gravitational forces pulling it inward, and it's going to expand. So we have two things happening now, two different things happening. The core is still contracting because the initial gravitational collapse is still occurring from when hydrogen was originally exhausted, used up. And the outer shell is now expanding due to the nuclear fusion in the lowest layer outside of the core. So the star has now become, it kind of has two parts to it, but we have a name for this star. It's become an old star. It's something known as a red giant. And stage 9 is the red giant phase, and now it has expanded beyond the orbit of Mercury if it was in the sun's current position. So if we think about our sun is halfway through its life. It's at 5 billion years out of the 10 billion where a star typically stays on the main sequence. In 5 billion years, if humans are still around, that's a big if, then we are going to need to find somewhere else to live because the sun is going to expand to a point where Earth is no longer going to be livable. Once the star even starts to enter into its red giant phase, it's going to, if we looked out in the sky, it would span 1/3 of the sky. So think about how much sky you can see right now if you walked outside, and 1/3 of that would be sun. So obviously it's going to be a lot closer to us. The outer layers are going to be a lot closer to enough. It's going to heat up the surface of the Earth enough to melt every metal, every object on the surface, and boil away our oceans and rip away our atmosphere. So Earth is not going to survive the sun going to its second, or the beginning of its death, which is the red giant phase. All right, so something really interesting happens. Remember, our core is still collapsing even though the outer layers are expanding, and something really interesting happens when the core gets dense enough. The helium core usually has to follow something called the ideal gas law, which we don't talk about in this class, but basically what it says is that as pressure and density increases, then the temperature is going to increase as well. But at some point in that contraction, the core actually gets dense enough so that the pressure of the electron shells will not allow the core to contract anymore. So it's not going to get any smaller, the pressure will not increase, but the temperature is going to continue to climb. It's going to continue to get hotter and hotter. So at this stage, we say that the core has become something called electron degenerate, and it no longer behaves like an ideal gas. So it acts more like a liquid, which means that it's able to heat up without expanding. So in other words, that self-regulating thing, that self-regulating mechanism that keeps main sequence stars so stable is now turned off because it's become electron degenerate. So in addition to becoming electron degenerate, the layer just outside of the inner core is now fusing hydrogen into helium, and the helium is now sinking toward the core just like it did it before at the beginning of this lecture when it was just sinking to the center of the core of the star. Now it's sinking from the outer layer onto the core, so the helium that's formed in that outer layer is going to continue to pile mass onto this incredibly dense core, increasing its mass, increasing its density, and then also increasing its temperature. So eventually, the star is going to reach a temperature of about 100 million Kelvin, the center of the star, and this is the temperature that is required in order to have helium fusion occur. Remember, helium fusion is going to require higher temperatures because it's a heavier element, and it's going to require greater speeds for the atoms to smash together in order to combine into something else. So helium fusion, as you can see on screen, is called the triple alpha process because it takes 3 helium nuclei and makes it into 1 carbon atom. So before we were fusing hydrogen into helium, now we're fusing helium into carbon. There are some intermittent steps in between that process where it becomes beryllium, but the ultimate end result is going to be carbon. And just like before with the hydrogen nuclear fusion process, the resulting carbon atom is going to weigh less than the combination of the beryllium and helium atoms that formed it. So some of that mass is going to be released in the form of energy as well. So this process it keeps it in its stability for a little while with that helium fusion occurring, but it's not going to last as long. It's certainly not going to last on the red giant branch for 10 billion years. And the reason is that the triple alpha process, that helium fusion process, is highly temperature dependent. So just doubling the temperature of the reaction causes it to run about 1 trillion times faster. So it's not going to last very long here. The helium is going to burn up very quickly. So as the fusing helium heats the core, which still cannot expand to cool down because it's still in that degenerate state, then the increased temperature is going to cause the helium fusion to proceed millions and millions of times faster, which is going to very rapidly heat the core, which in turn causes the helium to fuse again faster and faster and faster. It's a vicious cycle, just kind of takes off. And the ultimate end result of this is that the center of the helium core is going to explode. About 6%, 5 or 6% of that helium core, which now weighs almost half of the mass of the sun, is entirely fused into carbon within just a few minutes. So this this is like burning about 10 Earth masses of helium per second. And for obvious reasons, this is something called the helium flash, where helium begins to fume extremely rapidly. And within hours, this process is over. Within just a few minutes, the flash releases as much energy as our current sun generates in over 200 million years. So at the height of the flash, the sun's core will very briefly equal the combined luminosity of all of the stars in the Milky Way. It's over 1 billion stars. So this is a super energetic process, and during the helium flash, the star's core is heated so intensely that it essentially vaporizes. The individual nuclei are moving so fast that they can really just boil away and escape. So the core reverts back to a normal gas and then powerfully expands. The enormous gravitational energy that's needed to expand all that mass out of degeneracy, allow it to expand again and up to several times the original volume that they were before, is about the same energy that we experienced already during that helium flash. So this is a very energetic process, one of the most violent processes that our sun will experience. So eventually, the star's structure is going to catch up with that flood of energy that's dumped on it by that helium burning. The core expands, its density drops, and equilibrium is going to be restored. So the star is going to return to a type of a red giant, but we call that a horizontal branch now to distinguish it from asymptotic giant branch to distinguish it from the red giant that it was before. So now we're stable again after that giant helium flash. And now as helium continues to fuse into carbon, we start to have carbon in the core. And again, carbon is not going to be able to do anything because the temperature is not going to be hot enough. So we have, eventually we're going to use up all of the helium and we're going to have carbon. The carbon core, again, this process is going to repeat. It's going to shrink in size and then it's going to heat up as gravity pulls it inward. That's going to cause the outer layers, those hydrogen burning shells and helium burning shells, to expand as well, and they're going to to collapse as well, and they're going to heat up. So the star now has a couple of different layers. We have a contracting carbon core surrounded by a helium burning shell, and that in turn is surrounded by a hydrogen burning shell, and then we have the expanded envelope back to a giant star. So this process is where it ends for a star, for most stars. For stars that are around the size of our sun, that have the mass of about our sun, this is where it ends. There's not enough mass, there's not enough gravitational forces as this core collapses, to heat up the core of the star to a point where it can burn carbon, to the point where carbon fusion can occur. So eventually, that heat is going to stop. Gravity is going to take over. It's going to condense as much as it condenses. It's going to condense down to that electron degenerate state again at the center. But there's not going to be any other processes that occur that allow that heat to happen. So the temperature that's needed to reach carbon fusion is about 600 million Kelvin. And this doesn't happen for stars that are around the same solar mass. So there's no more outward fusion pressure being generated in the core. So the core of the star is essentially dead. The outer hydrogen and helium burning shells continue to consume fuel at an increasing rate, and as it expands, cools, and reascends onto that giant branch, the star begins to fall apart. So, driven by that intense radiation from within its outer layers, in those outer burning shells, the hydrogen and helium that are still pushing outward, the core is going to be left behind because that's essentially dead. There's no processes that are going on there, but those hydrogen and helium burning shells are still pushing outward. It's going to cause the star to expand, and since there's not much gravitational forces happening anymore, its outer layer is going to begin to drift away into interstellar space. And this last process is called stage 12, the planetary nebula. So this former red giant now consists of two distinct pieces. We have the exposed core, which is really hot and really luminous. And then we also have the escaping gas envelope, which is super pretty, as you can see in the pictures there. But it's really the death of the star. It heats up the outer layers of the cloud, and then gives us that spectacular display of the planetary nebula. So what's left after the planetary nebula has completely escaped is going to be just that dense nucleus core. And this is the death of sun-sized stars. Our sun is not going to explode in a supernova explosion. It is going to die quietly as a planetary nebula, and then the remaining core is just going to be that extremely dense and extremely hot, but very small white dwarf star. So our sun will end as a white dwarf. It's only bright because it is still very hot, but eventually, without anything to keep it hot, without any internal processes happening, it's going to continue to cool. And as it cools, it's going to lose its luminosity as well. It's just going to get dimmer and dimmer and dimmer and eventually cease to glow. So right after that planetary nebula goes away, it's a white dwarf star, and then as it gets dimmer and dimmer, it leads into a brown dwarf and then ultimately a black dwarf star. So this is the full evolution of a sun-like star. Like I said, our sun is or maybe I didn't say it, it's an average-sized, middle-aged star. It's very average in every sense of the word. And this is the evolution that it will take. It will die quietly. It will just give off its outer layers, end as a white dwarf star, and then ultimately a black dwarf star. They can never fuse. Stars around the size of our sun can never fuse hot enough for fusion past oxygen, and our sun can't fuse past carbon. So for more massive stars, though, you continue to have those periods of stability and instability. And in each new phase of nuclear fusion, because we can fuse heavier and heavier elements, the heavier elements, the star's central temperature is going to increase, the nuclear reactions are going to speed up, and the newly released energy is going to support the star for shorter and shorter periods of time. So this is the HR diagram for more massive stars. It has enough mass so that it can increase in temperature to fuse things past carbon, past oxygen, and then all the way up to iron. And I'll talk about why we can't get anything past iron in just a second. But the more mass of the element, the faster that fusion process happens, the more unstable the star is, and the shorter amount of time it can spend fusing that particular element. So it remains relatively stable while that fusion process is occurring, but the heavier the element, the shorter time it can maintain that type of equilibrium. So just for example, a star that's 20 times more massive than the sun would burn hydrogen for maybe 10 million years. 10 billion years. Helium for maybe 1 million years. Carbon for 1,000 years. Oxygen for maybe just 1 year. And then silicon next on there for about a week. And then when it gets to iron, the iron core might be able to sustain itself for less than a day. So the heavier the elements, the shorter and shorter amount of time. And once the inner core begins to change to iron, our high mass star is going to be in trouble. Nuclear fusion involving iron does not actually produce extra energy because the iron nuclei are so tightly bound that the energy cannot be extracted by combining them into heavier elements. So iron essentially is going to put out the fire in the core of the star, and the star's internal support is going to go away forever. So the star's foundation is destroyed, equilibrium is gone forever, and even though the core temperature of the star is going to be super, super high at about several billion Kelvin, the enormous gravitational pull from this high mass star is going to ultimately result in something called a supernova explosion. And the way this happens is it starts with a contraction. So the explosion outward begins with a contraction inward. Gravity is going to take over once those core reactions stop, once it gets to iron, and that's going to overwhelm the temperature, even at several billion Kelvin, and the star is going to implode. It's going to fall at itself. So the core temperature is above, it's billions of Kelvin now, and at these temperatures, individual photons are actually going to be energetic enough to split iron into lighter nuclei and then break down those nuclei apart until only protons and neutrons remain. This is a process in your notes that's known as photodisintegration. So at this point, the inner core of the star is taking on processes that release energy instead of producing it. So the heavy atoms are broken apart, and the individual electrons and protons are being slammed together at really high speeds. Electrons are negatively charged, protons are positively charged, and when they're slammed together, they cancel each other out and combine to make neutrons and release another type of particle, a high energy particle called a neutrino. So energy is streaming away from the core, and eventually what we have is a bunch of neutrons that are contracting and colliding and being pulled together. And you might guess that what we're going to end up with is something called a neutron star, and that's how it gets its name. But that's going to be for the next lecture. So the collapse is occurring at incredible speeds, just about at the third of the speed of light. So it's collapsing, and eventually we get to this density of about 10 to the 14 grams per cubic centimeter. This is just about the density of an actual neutron or the density of an atomic nucleus. And at this point, it's really interesting because if you think about having a density of a nucleus, then how would you know? Okay, so think about if you were able to fly down into an atom. How would we know if we were standing inside the nucleus or outside the nucleus if the density is the same inside and outside of that nucleus. So the only way we would know if we were inside or outside of that is if the density would change. If the density is the same inside and outside of that, the nucleus of an atom, then we wouldn't really know the difference. So essentially, the core of the star has become one giant atomic nucleus, which is super cool. So at this point, there's actually an outward pressure that's trying to stop the collapse, and it's actually a process that goes on inside of the nucleus of an atom all the time, and it's a type of energy called nuclear binding energy. Nuclear binding energy usually works to pull the nucleus together, to keep the nucleus together, but it can also act in the opposite direction, trying to pull things apart. So the nuclear binding energy sees all the mass rushing in at a third of the speed of the light and tries to stop it. But that process is happening so quickly that it actually overshoots, it overcompensates, and it sends that energy back out in the opposite direction at about half of the speed of light. So the core is essentially rebounded from its collapse and is now flying back outward. The way I picture it is always like a slow motion video of a ball hitting a wall, just that collapse, and then all of a sudden it just overcompensates in the speed trying to push it back out, and then it explodes. This rebound mechanism has so much energy that it blasts all of the remaining material out into space, and that is a supernova explosion. So a star around the size of the sun is going to die quietly. A star of more than about 8 solar masses, 8 times the size of our sun, can fuse things beyond carbon in its core, and eventually that process is going to happen where it collapses so fast that nuclear binding energy takes over, sends all that material in the opposite direction, and the star explodes. So that's where I'm going to leave it for today. Star formation is cyclical. Stars form in the interstellar medium. Stars evolve throughout different stages of their lifetime, and then they die and send heavier elements that they created in the core of the star back out into the interstellar medium. And then those elements that are sent back out become part of the interstellar medium, and then new stars are formed from that interstellar matter again. So it's a very cyclical process that happens over and over again, and just like the last sentence here, and so it goes. All right, so just as a recap, at the beginning of the session, this was sections 2 and 3 in your course notes. I have another session on Wednesday morning. I think I'm going to talk about quantum mechanics, and then I'm going to add a third session for later this week, just because we have so much material to cover. We're going to talk about special relativity, general relativity, black holes, and neutron stars. All right, so that is all I have for the evening. Thank you, Trayvon, for coming. Thank you, anyone else who listens to the video recording. I'll stick around for a few more minutes if you have any questions, and if not, then you are free to go. I hope to see you at the next one.